Thank you very much, Raffaele, for this very kind introduction. So also thank Raffaella, Ginesta, and Heather for inviting me here. It's a great pleasure. I've been interacting with all of you, and I hope to interact more with you in the future. And perhaps this is also a good opportunity. In fact, this is a conference that I've been looking forward for quite some time. So I will be talking about hypergraphs. Hypergraphs are maybe generalizations of networks. And today I found out that I'm not even good at networks because I got confused with the London Underground network and I got on the wrong subway. And it took me quite some effort, 4 or 5 different trains to get here in the end. But nevertheless, I managed. So perhaps affiliations are no longer completely accurate because at the Max-Planck-Institut, I got recently kicked out for age reasons. Well, anyway, so small joke in the beginning. So I will now, you can see it all right. Yeah, I can't really see it on my screen here, but that is okay. I don't know, maybe I just take this one because usually I have the habit of walking around. And so we want to probe structures. In fact, I will try to give a rather general talk because this is the introduction, so I would like to open a general perspective. So when you probe a structure, if you're a physicist, you want to identify important and interpretable features that are easy to compute in order to study your structure. That, of course, is usually very successful. But as a mathematician, you want to derive them from abstract principles. And that is what I will try to do today. So let's start in the most abstract way. We have a very basic category. So a category consists of objects and morphisms. And we just have 2 objects here and 1 non-trivial morphism. So objects are called 1 and 0. This is standard notation in category theory. Besides the identity morphisms, which are always there, we just have 1 non-trivial morphism. So then we have a functor from this category to sets. So we associate sets to both objects and also map between sets to the morphism. So that is, we have now 2 sets, R and U, and we have a map between them. And for this talk, I will always assume that R and U are finite because I don't want to deal with issues of compactness, convergence, and so on here. So for our purposes, in fact, the target set U has somewhat more structure. Namely, it is a power set of another set, the set of subsets of some set V. It could also have some other structures, but for hypergraphs, this, I think, is a basic option. So that is to each element in R, which is a relation, and which will later on be a hyperedge. In a hypergraph, we associate a set of elements of V. V, of course, indicates that we are speaking of a vertex set here. And so without loss of generality, of course, we assume that V is covered by all the images. That is a basic hypergraph. So in other words, a hypergraph is a cover of a vertex set V. Yeah? Now and in fact, of course, if every relation has precisely 2 elements, we have an ordinary graph. So that is very abstract, but in a sense also quite trivial. So now what can we do there? So first of all, from such a hypergraph, we consider a simplicial complex, namely its check complex. So that means that the vertices of this check complex are the elements that are the images of our relations. That is subsets of V. And so then whenever K plus one of these subsets have a non-empty intersection. That is, if they share a simplex, then we insert, if they share a vertex, then we insert a k-simplex. So that obviously gives us a simplicial complex, and then we can then use that simplicial complex to derive certain invariants. For example, we could compute its Betti numbers, or more generally, we can look at the Ekman Laplacians of the simplicial complex and evaluate the eigenvalues, that is spectra, and then the eigenvalues of these Laplacians constitute invariants of the hypergraph H. We could even be a little more general. So U need not necessarily be a power set of another set. It can also be a set of objects of some other category C, which has some commutative and associative relation. And then we have some map to 0, 1, and we assume that whenever the intersection or the wedge of two elements gets the image 1, then they also individually have the image 1. And then, this is as before, we can assign a k-simplex to any configuration, k plus 1, consisting of k plus 1 objects, that is mapped to 1. And again, we obtain a simplicial complex. And in fact, this could even depend on a parameter. We just need to assume that when the parameter is increasing, the relations that are mapped to 1 is growing, and then we obtain an increasing family of simplicial complexes as in topological data analysis. But that is not really what we are interested in. We want to look at a dynamic situation instead of the static configuration that I have been looking at before. So we enrich our category. Now we have two non-trivial morphisms from the object 1 to the object 0. And again, we map that to sets, so we associate sets. And now we have two maps, HI and HT. I stands for initial and T stands for terminal, from R, the set of relations, to U. And of course, this now gives us a directed graph. And now R is the edge set, and U, the vertex set, contains the vertex sets, and the two arrows map an edge to its initial and its terminal vertex. That is how a category theorist would describe a graph. But again, we don't want to look at ordinary graphs, we want to look at hypergraphs. So again, U is a power set of some other set, or as I had indicated before, it could be more general if we wanted to have it. Yeah. So now to each hyper-edge, we associate two sets of elements of V, the input and the output of the hyper-edge, or the initial and the terminal set of the hyper-edge. And so this would be a directed hypergraph. So a directed hypergraph consists of two families of subsets of a vertex set V. And then, of course, then we get an induced map. So the initial set can always be mapped to the terminal set, but however, this does not induce, in general, a simplicial map of the check complexes. And therefore, we should construct other invariants than those coming from these check complexes. So that will be the main point here. And in fact, we shall ignore the directions. I will explain that a little later and just also include the reverse directions and speak of orientations. And we call this a chemical hypergraph, and that was explored in particular in the PhD thesis of Raffaella, on which much of what I'm reporting here will build. So an oriented hypergraph, in an oriented hypergraph, one hyperedge can carry two orientations corresponding to the two directions, whereas for a directed hypergraph, a hyperedge would be allowed to go in only one direction. So here are the pictures. Again, I think they were created by Raffaella. This is the static picture on top, where we just have a vertex set, And here's a dynamic picture where we have a relation between two vertex sets. So for example, the top one could be the input set and the bottom one could be the output set. But I'm not indicating a direction here because, as I said, I want to treat both directions equally, not just because I want to do it, but it will naturally come out of the formalism that I'm going to develop. So here's a hyperflower. Again, a picture created by Raffaella. So this is a standard example during the stop. So we have a group of central vertices here, 10 central vertices, and then we have 5 hyperedges, and each hyperedge links the group of central vertices to a particular group of 3 peripheral vertices. So the central vertices are included in all hyperedges, and each group of peripheral vertices is included in precisely 1 hyperedge. So that is the structure here. It's a rather simple structure, if you see it here, but exploring it will already provide us some insight. So, but before I go on, now this has been quite abstract, and maybe not everybody will enjoy that level of abstraction that I'm developing here. So as an interlude now, I present a concrete example that we're also working on, namely chemical space. So chemical space consists of all chemical substances connected by chemical reactions. So a chemical reaction connects a set of educts or the substrates with a set of products. And so thus a reaction is an edge connecting 2 hypervertices. So in fact, that was maybe our prime motivation to try to develop a theory of hypergraphs, because we wanted to understand, and we still try to understand chemical space with the mathematical tools that we are developing. And one can ask many questions. So what is possible? What reactions are possible? You can ask what is currently known, which reactions do chemists know, they have reported in the literature. And you can also ask the historical question, namely, how did it evolve? And we try to ask all these questions. And we need some database for that. So chemists are very systematic people. In fact, they seem to be much more systematic than mathematicians or physicists in that regard, because they started to record already in the 19th century systematically in handbooks what was known about all chemical reactions and substances that were known at the time. And these handbooks were updated every few years in the beginning and every year later on. Of course, that became a little too large in the 20th century, and eventually these 2 handbooks were bought up by Elsevier, and they were converted into an electronic database, an access database, to which we in fact have privileged access. So for example, already 7 years ago, more than 40 million chemical reactions were known, and more than 20 million substances were recorded in the access database. In fact, there are other databases that have slightly different numbers, but that just indicates to show you the magnitude or the size of the hypergraphs that we really want to understand. And also, since this is yearly resolved, we can also trace its evolution over time, so for a period of more than 200 years. As I already said, chemists are more systematic people than mathematicians or physicists. So we don't have, at least as far as I'm aware, anything comparable in mathematics or physics. But of course, it would be quite beautiful to have something like that, because that really allows us to trace the history of an entire field of science. And in fact, as you may not know, chemistry is a field that occupies most scientists. Many more chemists around than physicists or mathematicians. So in a certain sense,
how much more?
Perhaps 3 or 4 times more, that order of magnitude. Yeah. So in that sense, maybe chemistry is a kind of paradigmatic for the evolution of science. And so perhaps what we learn about chemistry can then also be generalized or extended to other fields if we had a comparable database. In biology, for example, you have the species and you have the proteins, but that is not really comparable to the chemical database. So here are some pictures. So we have an exponential growth of new compounds that is indicated here, was just briefly interrupted by the two world wars. So that is the First World War and that is the Second World War, but it quickly recovered afterwards. And so it really has a very regular exponential growth path. And you can resolve it to different domains of chemistry that is shown on the right graph. But the left one is the one that is of most interest for me. So we then have a growth model. So first of all, if we return to that, we see that the growth rate has been almost constant over more than 200 years. So that is a phenomenon that requires explanation. Why is that so regular? The growth rate is a little above 4%, but essentially it has been the same for more than 200 years. Why is that so? And there have been many shifts. Number of chemists, for example, is not really following the same pattern, and the economy was much more disruptive. Science funding was much more disruptive. There have also been substantial changes, both in chemical techniques, chemical synthesis and analysis, and also there have been major shifts. In the 19th century, up to the First World War, chemistry was dominated by German chemists and institutions. After that, it shifted to the United States. 1920s and 1930s, it shifted to the United States. And then after the Second World War, was largely dominated by the United States. But nowadays, it seems that Chinese chemists are those that publish most papers. So another change is taking place. But none of that really affected profoundly the growth rate. So why is that so? And that is something that we want to understand. We're working towards it, but we don't yet have the full solution. But we have a couple of insights already. But I will not go too much into this. I will just present you some very simple growth model. Exponential growth model, of course. And in fact, if you look at it more closely, we can distinguish three different periods. Essentially, they're characterized by a change in variability. If we go back to this one, until about 1860, the variability was pretty high. And in fact, essentially constant over that period. Then there was a middle period where the variability dropped. In 1860, it dropped relatively sharply. Then it stayed constant for another 120 years. And in 1980, it dropped again. So we can distinguish by statistical analysis 3 periods there. And of course, our chemistry colleagues try to identify which events caused that. So the first one was probably caused by the introduction of the structural theory, Kekulé and this benzol ring, so that you could conduct your experiments much more systematically. And in 1980, there was an advance of high throughput analysis, which also was a profound change in chemical technology and which probably caused that further drop of variability. And also the substances that people were interested in changed. Until 1860, they were essentially uniformly interested in everything. And in 1860, the so-called organic regime started. People were mainly interested in organic substances that dominated chemistry. And in 1980, then started what we call the organometallic regime, where people were mainly interested in combinations of organic substances with various kinds of metals. So we have this growth model and the 3 periods. And as I already explained, they can be distinguished by what the chemists were interested in. And as I said, the statistical analysis shows rather sharp and sudden transitions between the regimes and caused by structural theory and high throughput analysis respectively. And you can also look at other things, the distributions of compounds and so on, look at statistics there, which we are still further exploring, but I will not go too much into the details here. Because now I want to come back to the abstract picture after this small interlude. I just wanted to show you that what we are doing here, what you are doing here will have real applications in different fields. And in fact, in a field that may be as far removed from your own interest as the history of science. So now we had developed this dynamic picture, and now what we can do with that as a mathematician. So there are two things that one can do. I will mainly concentrate on the first one. So usually whenever you want to probe something mathematically, you try to do some linear theory. That is well established in mathematics, so we also do that here. So we associated Hilbert space, L2 of U, of functions to the target. So that is, we look at functions defined on the elements of our space U, and then we introduce some scalar product, and we can choose some weight, whichever weight we want in principle, but of course it should be naturally related to the structure, so we have a scalar product. And then we can let R operate on this L2 space and see what comes out. The other one, for which I will probably not have that much time, is that one looks at local quantities that encode how the elements of U are related to the operations of R, and then look at their statistics. That would be a nonlinear method, and the slogan here is curvatures, because it was originally inspired by notions developed in a very different field in Riemannian geometry. But as I said, probably I will not have enough time to speak about that at some point. You need to stop me, Raphael, that I don't go forever. So let's explore the first method. So we had these two relations, HI and HT, the input and the output of a hyperedge, and then we have a function on U, and then, of course, we can look at the difference here. That is the most natural operation. So we look at the function evaluated on the inputs, sum them all up, and then subtract the function evaluated on the outputs and sum them all up and look at the difference. So that is the most basic operation that we can think of. And of course, when we exchange the initial and the output set, we get a minus sign. And so therefore, we should consider oriented relations, and we denote the change of orientation also by a minus sign. So when we go from R to minus R, it just means that we exchange the output and the input of a relation. But that will come up naturally here. So now we have these differences. They have certain properties. So if the terminal set of the first reaction is the initial set of the second one, if the terminal set of the second one is the initial set of the third one, and finally if the terminal set of the third one now is the initial set of the first one, so that should be a 1 here, then we can sum them up and get 0, obviously. This is trivial, but it already shows that there is something useful behind that here, because now this operator annihilates cycles. Of course, we cannot have longer cycles, they are also annihilated, and so that indicates that there should be some relation to algebraic topology. Now, we have this difference operator, and so now we also define a product on functions on R, on the relations. Again, we can introduce, if we want so, certain weights, and then we can obtain adjoint of this operator. Yeah? Operator and to scalar product, so we have an adjoint of this operator. And now, since the difference operator is antisymmetric, this adjoint vanishes on symmetric elements. And so therefore it suffices to look at antisymmetric elements on the relations. So that get a minus sign if we go from relation to the opposite relation. If we go from R to minus R, then the elements obtain a minus sign, because the other ones, the symmetric ones that don't get a minus sign, are automatically annihilated and they will drop out here. So that is really the mathematical reason why we can go from directions to orientations. Of course, if we also want to include symmetric ones, we should choose a delta that is not antisymmetric, that has some other properties, but that remains to be explored. But that seems to be the natural way of getting invariants that really encode also the directions. So we have the boundary operator, we have the co-boundary operator, and so we can combine them, and then we get the Laplace operators. We get two Laplace operators because we can combine them in arbitrary order. We can first go from U to R and then go back from R to U. That gives us an operator on functions on U. Or we could start with R, go to U, and go back to R. That gives us an operator operating on functions on R. And of course, now, just by way of construction, we have these relations which tell us that the operators are symmetric. So this one is equal to this one here. So likewise, this one is equal to this one. So they're symmetric. And also here in the intermediate line, we see that if f is equal to g, we get a square. So both operators are also non-negative. And also since they're just combinations of the same operators in opposite order, the non-zero eigenvalues coincide. So that is the setting now that also gives us a Laplace operator on hypergraphs, which in fact was the subject of the thesis of Raffaella. So I've sketched the abstract principles, but now I will also explain a little more concretely how this proceeds on hypergraphs. So I will recall the individual steps in more concrete terms. So first of all, we need to choose weights. So we just choose weight 1 on the hyper edges and give a certain weight to each vertex. So for each hyper edge, we can consider the number of vertices contained in an hyper edge. And then for vertex contained in the hyper edge, we want to record how many other vertices are contained in the hyper edge. So we subtract 1. Yeah, and then we sum over all hyper edges that this vertex is contained in. So that is what we might call the hyperdegree of a vertex. Again, this is a little arbitrary, but it seems to be a rather natural choice of weight if you look at hypergraphs. Of course, we could also look at weighted relations and then have other additional weights, but that wouldn't really affect the abstract principles of the theory here. Then we define scalar products for functions on hyper edges and for functions defined on vertices that are based on the weights. And then we define the boundary operator for function defined on vertex weights and mapping them to function defined on hyper edges. We define the co-boundary operator based on the scalar products. And we define the Laplace operators as the two different compositions of the boundary and the co-boundary operator. Boundary composed with co-boundary or co-boundary composed with boundary. These are the two Laplace operators, just more concretely implementing the abstract principle I had developed earlier. So here are our scalar products, as I had already indicated. So for the hyperedge product, we just choose weights 1. And for the vertex products, we choose hyperdegrees. And then we have the boundary operator. This is the difference operator as before. And we have the adjoint operator, which now becomes this one. So for each vertex, we look at all the hyperedges for which the vertex is an input, sum up the contributions, and subtract the contributions for all hyperedges for which the vertex is an output, and normalize it by the hyperdegree. And then we have the Laplace operators. Looks a little complicated, but the point is that this is really derived from abstract principles. So we really compare at the vertex what comes in and what goes out with the appropriate signs. And likewise, we do the appropriate thing for the hyper edges. But instead of discussing this formula in detail, I will just look at the case where we have an ordinary graph, because then it's easier to understand. Because for an ordinary graph, this one reduces just to what is called the normalized graph Laplacian. So for a function on the vertex set, when we evaluate its Laplacian at the vertex, we compare the value at the vertex itself with the average of the values at all its neighbors. Now that is important thing. So that is the average of the neighbors, and that is the vertex itself. So we just compare the two, and of course that also suggests that we are looking at random walks, where a random walker can go in all directions, with equal probability, and so on. So or we can look at it as a generator of a diffusion process. We have some substance that at time 0 is concentrated at the vertex V, and then randomly diffuses or equally diffuses to its neighbors and so on. And we can iterate and repeat that. So this operator generates important processes. And likewise, then we can evaluate the operator on edges. Again, we have this anti-symmetry here. And so then we again compare what comes in at the edge at one end and what flows out of the edge at the other hand. So again, from point of physics or whatever, this is a very natural operation that really quantifies the flow through a network. And as I said, our construction has led to a natural generalization of these processes to hypergraphs. So, of course, they have the same non-zero eigenvalues, and the multiplicities of the eigenvalues then just encode the most basic quantity on a graph. It's just the Euler number, the number of vertices minus the number of edges. And so that is the difference of the multiplicities here. Of course, that reminds you of other general principles or in Riemannian geometry and algebraic topology. Well, if you look at the hypergraphs, there could be, from a chemical point of view, there are catalysts that are contained in both the input and the output set, and they cause an eigenvalue 0 for the zero Laplacian. And so there are more eigenvalues 0 for the zero Laplacian on hypergraphs than there are on ordinary graphs. And likewise, closed systems of reaction cause an eigenvalue 0 for the one Laplacian on hyperedges. So already the eigenvalue 0 detects some kind of information, or the multiplicity of the eigenvalue 0 detects some kind of information about the underlying hypergraph. And bipartiteness causes large eigenvalues for an ordinary graph. Well, it's a very basic and simple fact that this Laplacian that I've indicated here, this Laplacian delta 0 has the eigenvalue 2 if and only if the graph is bipartite. Because then you can really have opposite behavior. So f of v can be +1 and f of w can be -1 for all the neighbors, and then you get the eigenvalue 2. For graphs that are non-bipartite, you cannot have the eigenvalue 2. And for non-bipartite graphs, all eigenvalues are smaller than 2. And so, again, not only the eigenvalue 0, but also the largest eigenvalues give you some information about the structure. So let's evaluate that on the hyperflower here on our standard example. Let's recall it. So we have a group of central vertices, 10 in this case, and we have a couple of hyperedges, 5 in this example, and each of them contains a distinct group of 3 peripheral vertices. So what are the eigenvalues here? So first of all, in fact, we can not only compute the eigenvalues, we can also construct the eigenfunctions, and that gives us information. So if you want to find them, you usually try very simple things. So we put just -1 on the central nodes and +1 on all the peripheral nodes. And in fact, that gives you an eigenfunction for this eigenvalue, c plus t over c plus t minus 1. And that is the largest eigenvalue that we can get here. And in fact, that is caused by the opposite behavior. So the eigenfunction behaves oppositely at the center and at the periphery. Next one, we put it +1 on one leaf, +1 here, and -1 on another leaf, for example, over here. And we put it 0 elsewhere. And again, that gives us an eigenfunction. The eigenvalue is smaller. So now it's only t over c plus t minus 1. The first one was c plus t over c plus t minus 1, so it's smaller. And so this is a balance behavior, balance between the peripheral vertices, and that gives us intermediate eigenvalues. And the remaining eigenvalues, eigenfunctions, all have the eigenvalue 0, but there are different types of them. So first of all, we can have one that doesn't change sign. Just to normalize it, we put it 1 on c here and 1 on t on the peripheral vertices. And that, in fact, gives the eigenvalue 0 because just the value at each vertex is equal to the average of the values of its neighbors with the appropriate normalizations that we are having here. So this does not change sign. Then there's another way. We look at one component, be it a center or a leaf. We just pick out 2 vertices. We put the function equal to +1 on one of these nodes and equal to -1 on the other nodes. And again, that gives us an eigenvalue 0. And so that just means that 2 inputs or 2 outputs compensate each other. And so that is really different from ordinary graphs. In ordinary graphs, the Laplace operator satisfies the maximum principle here. Yeah, but on hypergraphs, it no longer satisfies the maximum principle because you can have this compensation effect. And so that way, we have computed all the linearly independent eigenfunctions. You have as many eigenfunctions if you have degrees of freedom, and the degrees of freedom on vertices, of course, that's the number of vertices. And so we have easily determined all the eigenfunctions and all the eigenvalues of that, and we can also understand the behavior, what this is doing on the hyperflower. And so the spectral analysis gives us precise information about how to decompose function spaces and what are the natural decompositions on function spaces. Of course, you also have certain invariances, so you can relate it to group actions and so on, which you can easily do, but which I will not do here. So I will rather present an application. Look at coupled chaotic oscillators. In fact, it was a fundamental discovery of Kunihiko Kaneko, if I understand it correctly, was the first one to notice that chaotic oscillators that are diffusively coupled can synchronize. Just if you think about it, a chaotic oscillator really is chaotic. Yeah. So look at people. So they can be really chaotic, but under certain synchronizations, certain couplings. For example, if you go to a soccer stadium or so, all these chaotic people somehow synchronize, all these 50,000 spectators or so. Yeah. And so how does this come about? Yeah, all the individuals still behave chaotically. If you look at each individual, you cannot really tell, but all the people, all these chaotic people are really doing the same. How can something like that come about? Or if you look at, I mean, there are this famous example of the fireflies that synchronize, maybe they're not so chaotic, but the neurons in your brain can also synchronize. That is very important for object recognition and feature binding. So neurons in different regions synchronize, and the behavior of an individual neuron can also be quite complicated, if not chaotic, but nevertheless, coupling mechanisms that can synchronize them. So what Kaneko did, he considered functions on a vertex set with a time index. The n stands for time. And so they're coupled, first of all, by some function. F is a function that generates chaotic behavior. I will give you an example in a moment. But then you diffusively couple them by the Laplace operator with some parameter epsilon that is between 0 and 1. And again, here's the Laplace operator that we had before, the normalized Laplace operators. And the dynamics become synchronized if x, the state, becomes independent of the vertex v. And then for all future times. And in fact, f is chosen as a chaotic function, and the paradigmatic chaotic function is a tent map. Probably, since you're all aware of that, I don't really have to explain that in much detail. So here's a tent map. And you can, if you then multiply it by some parameter sigma, you can compute its Lyapunov exponent, which is logarithm of 2 sigma for this iteration. And in fact, then you can determine the condition for synchronization, and that turns out to depend on the eigenvalues of the Laplacian. So the first eigenvalue should be sufficiently large, which essentially means that it is difficult to split up the network into two components by cutting few connections. And it should also be bounded away from 2, because we don't want to have a bipartite network, because they could have period 2 oscillations. Then, in fact, many years ago with a postdoc, I determined that condition for sufficient condition for synchronization. So you start with arbitrary initial values. The chaotic oscillators need not be synchronized at the beginning, but eventually they will become synchronized, or more precisely, the synchronized state is stable. Now has a non-trivial basin of attraction. That is what this condition yields. So this is a surprising phenomenon, but on the global state where everybody is doing the same may not be so interesting. So if you watch the spectators in a soccer game, since they're all doing the same, maybe that is not so interesting after all. So we rather want to have something where a global pattern emerges, but where still individual elements will behave differently from each other, but still in some way that is coordinated. And so therefore we studied coupled oscillators on hypergraphs with Raffaella and also with Christian Kühn in Munich and his student Tobias Böhle. So again, we have our hypergraph Laplacian now for the coupling. I'll just record the definition. And so again, we look at the flow through hyperedges where V is the input minus the flow through hyperedges where V is the output. So that is what the operator does, compares that. And we can write it in a somewhat more compact form, but maybe again, that is not so important here. The important thing is again that we can do the coupling. We have some chaotic function, tent map or logistic function or whatever you want, which by itself generates chaotic behavior, but when we have the diffusive, but then we have this diffusive coupling term with the Laplace operator. And so again, we do it on the hyperflower because we understand the hyperflower. And so we try to see what is happening there. And so that indicates, now this color code shows in which region the values actually are. And so this colorful picture indicates that we have chaotic behavior, but now we see that we have synchronization among all the central vertices, and we have synchronization among all the peripheral vertices, but the central and the peripheral vertices operate differently. We can also generate other behavior. So we have coordinated behavior on the central vertices, so they behave very, very regularly, but we have completely chaotic and uncoordinated behavior on the peripheral vertices. Or we could have such a situation, again, synchronization in each group of vertices, but each group behaves differently. So not only the center and the periphery behaves differently, but also all the peripheral groups behave differently from each other, just by choosing the parameters, the sigma and the epsilon appropriately. And here, again, is something different. So again, quite constrained and confined behavior at the center, and then some interesting behavior at the periphery, where two of the peripheral vertices are synchronized with each other, but the other one is out of synchrony, but shows a much smaller range of activity. And so, in fact, that seems to be a mechanism for generating very interesting and very rich coordinated behavior by looking at diffusive coupling, not on graphs, but on hypergraphs. Okay, perhaps I still have a few more minutes, or as I said, you need to stop me. Oh, sure, you need to stop me. So then I now come to the second part, the curvatures. And already what I said was in a certain sense inspired by what one knows in Riemannian geometry. My own background is in Riemannian geometry, but it was very natural for me to see to what extent the concepts developed in Riemannian geometry can be extended and are meaningful on more discrete structures. We had the Laplace operators, and they were already extended to simplicial complexes by Benno Eckmann in 1944. And then the spectral theory was studied together with my PhD student Daniela Horak, who in fact is working in London now, but in industry. So the point, of course, is that both Riemannian manifolds on one hand and graphs or hypergraphs on the other hand carry metric or geometric structures. And in general, it has been an important research direction also in geometry more generally in recent years to extend concepts originally developed in Riemannian geometry to more general metric spaces. And in fact, that is kind of a simplification because the concepts developed in Riemannian geometry are quite intricate. If you compute the Riemann curvature tensor of a manifold, that is a somewhat complicated formula. Depends on second derivatives of the metric. And of course, it was a genius of Riemann who found that this encodes all the invariants of a Riemannian metric in a very efficient and compact way. But to understand this requires some mathematical understanding. Whereas if you do these things on graphs, on more general metric space, it becomes much simpler. But the historical development was in the other direction. So, and as already said, curvature is the most basic invariant. And curvatures have been developed, also curvature notions have been developed in graph theory. Again, maybe curvature is not really a very good word there because, I mean, in which sense is a graph or is a hypergraph is curved? Just speak about curvatures because they're generalizations of concepts developed in Riemannian geometry. And even in Riemannian geometry, the history of the name is a little weird because in terms of really Riemannian geometry, a curve that may look quite curved in space, in fact, does have curvature 0. And there are 3 types of curvature in Riemannian geometry: the scalar curvature, the Ricci curvature, and the sectional curvature. And while we also look at sectional curvatures, which are very important concepts, it seems also in metric geometry and also in machine learning. Here we'll just look at Ritchie curvatures. And in Riemannian geometry, Ritchie curvature is assigned to tangent vectors. And since a vector is determined by 2 points for graphs, the analog of Ritchie curvature should be assigned to edges. And in fact, that is an important message that I also want to convey here. Many invariants in graph theory also have been assigned to vertices. But from my geometric perspective, the most basic and natural important invariants should be assigned to edges because they really express the relations. And quantities assigned to vertices should then only be derived quantities, like scalar curvatures that sum over the Ritchie curvature of edges that come together at a vertex. And so for hypergraph, curvature should be assigned to hyperedges, and Ritchie curvature in Riemann geometry controls expansion properties of volumes. We look at volumes of balls, distance balls as a function of the radius, and the larger the Ritchie curvature, the smaller the volume grows. This is a basic result. And it also is related to stochastic processes. If you have two random walkers on a manifold, if you want to couple them, if one moves left, the other one also has to move left, and so on, then the more positive the Ritchie curvature is, the easier it is for them to eventually meet. Yeah, so these are basic properties, and you can take them then as an inspiration for developing Ritchie curvatures on graphs. And let me now be brief here. We just look at two types of curvatures. On one hand, you have the Olivier curvature, which is related to the volume growth. So if you have vertices and you look at their neighborhoods, or if you have hypervertices and look at the neighborhoods, and you just record how much they overlap. And the more overlaps they have, the more positive the Olivier type Ritchie curvature is. For the Forman curvature, you look at each vertex, how many other edges or hyper edges are emanating from that vertex. In the upper left paper, the neighborhoods overlap because we look at the configuration here and the configuration here. The neighborhoods just overlap in a single vertex, so there's no non-overlap. So here, the Olivier curvature is positive. Here the neighborhoods do not overlap, so here the Olivier curvature is negative. Also here the Forman curvature is negative because not too many other edges are emanating here. Here the Forman curvature becomes negative because many other edges are incoming or outgoing at the vertices, but still here the Olivier curvature is positive because the neighborhoods overlap. And so these two types of curvatures then capture different aspects of networks, and we have used these properties and for the empirical study of different networks. And so now I can just acknowledge my collaborator, but foremost, of course, I should mention Rafaela here because her thesis was really the starting point of much, and we have collaborated on many other papers, which I didn't have the time to go into here. And we have completed a book manuscript also with Dung Zhang from Beijing University, which is currently under review. And Guillermo Restrepo and Duc are leading the analysis of the chemical data. We are collaborating with Peter Stadler also on chemistry. He's a bioinformatics chair at Leipzig, and mentioned the work on synchronization or diffusive coupling on hypergraphs with Christian Kühn and his student Tobias Böhle. I think with that, my time is over, and I thank you for your attention.
Thank you so much for this wonderful talk. Are there questions? Yes, Larry?
So, first, thanks for a beautiful talk. So for graphs, my intuition is that if you have like almost every large graph has zero Laplace eigenvalues close to 1, and if they're not, there must be some structure.
Yes.
And from the talk, it seems that this holds in general for hypergraphs.
Yeah.
Directly hypergraphs.
Yes.
That's correct.
Yes. Yes. I mean, eigenvalue 1 on a graph can be generated quite easily, namely by vertex duplications. You take a graph, you pick one vertex, then you make a new graph where you have a copy of that vertex that is connected to the same neighbors as the original vertex was. Then you have an eigenfunction that is +1 on the original and -1 on the other vertex, and that has the eigenvalue 1. So that is very, very easy process. And of course, you can also then try to do analogs for hypergraphs, and Rafaela has in fact studied some of these analogs. So that is, you understand how very simple processes generate particular eigenvalues, then you can use it for the reverse direction. If you have some structure, you compute its spectrum, and you see, for example, that the eigenvalue 1 has a high multiplicity, then you speculate that much of the structure has been generated by vertex duplications. Yeah, I mean, there are other ways to generate the eigenvalue 1, but this is the most prominent one. Yeah, and you can do the same on hypergraphs. Not all of that has been done systematically yet. So, I mean, we are still in the process of exploring hypergraphs empirically through the spectra. We have done in the past decades a lot more work on ordinary graphs, but the spectrum was already quite insightful. So the principle is you understand how particular eigenvalues emerge, or also why on particular types of graphs particular eigenvalues cannot occur. So for example, you can look at graphs that don't have the eigenvalue 1. Yeah, and then you can ask, how far can the eigenvalues be away from 1? What is the spectral gap at 1? Yeah, and so with Rafaela and Dung Zhang, we could classify those graphs that have the largest spectral gap. In fact, the graphs that have no eigenvalues between 1/2 and 3/2. Yeah, eigenvalue 1/2 and 3/2 occur, but nothing in between. And one can classify those. So those graphs. These are very particular graphs. And so then empirically, if you see a large spectral gap around 1, it gives you some indication already about the structure of the graph. Yeah, and of course, determining the graph exactly also is a very difficult problem. Most of these problems are in NP hard or perhaps even NP complete, but computing the spectrum, at least approximately with good numerical algorithms is pretty quick. Yeah, and so then but you need insight about the geometry behind the spectrum of a graph in order to interpret your findings, and that is what we are trying to develop.
Thank you, Juergen. Yes, Tina had a.
Yeah. Oh, so
You can go there first.
Okay. So I'm interested. So there's some work by Polterovich with connecting kind of geometry with persistence.
Yeah.
And I don't know if any of that connects with spectral properties. So I wondered if any of those kind of results in the last recent years connect to some of the hypergraph settings that you're interested in.
I'm not aware of any, but I would strongly assume that there is some connection, that there's something interesting to explore there. But perhaps you already know more about that than I do. Yeah.
I don't know. I just thought that some of the things we were discussing might be related on the theory side to build more bridges.
Yeah, I mean, certainly because the spectral invariants are very, very basic ones. I mean, from the Laplace operator, you already get the Betty numbers, yeah. And then the spectral invariants are more refined invariants. And of course, I mean, with TDA, you should naturally combine that, yeah. Yeah, you're not. I mean, there you just look at the Betty numbers, and I mean, you're an expert on this, on the barcodes constructed by the Betty numbers, but it might be worse than also looking at how the eigenvalues change, how the spectrum changes when you vary the parameter R. Perhaps some people have started to explore that already, but I think it will certainly be worth exploring it because it tells you something about the connectivity of the graph. not only whether it has cycles, but how easily you can decompose it. And I mean, there's these Giga-type estimates, which we are currently also extending to simplicial complexes. And so I think there's a lot more to explore.
We have 2 minutes. Yeah.
Very quick question. Excellent talk. I enjoyed it very much. This is about the second part of your talk where you were talking about Ricci curvature on hyper edges. Now, do real world hypergraphs have a skewed distribution when it comes to the Ricci curvature of the hyper edges?
There are particular aspects of the distributions of curvatures already for graphs, which empirical distributions, which tell us that other principles behind the formation of empirical networks and those advocated in the literature. I mean, you have this preferential attachment, you have the small world effect, but when you look at the distribution of Forman-Ricci curvatures already, which are very simple ones, then you already see some other patterns that are quite pervasive in empirical networks, but which are not accounted for by these processes. Again, that is something that we hope to explore in more detail. We see, as I said, we already see something there that needs some explanation. I think we have some ideas for graphs, and certainly something there should also exist for hypergraphs, but we have not studied that yet.
So you don't know for sure if there's a skewed distribution on the Ricci curvature of hyper edges that appear in hypergraph in real life?
No.
You don't know for sure.
Yeah, well, I mean, we have done some computations for Forman-Ricci curvature for the chemical hypergraph, but we have not yet evaluated the results yet. And of course, you should look at other hypergraphs, for example, from social networks to get many hypergraphs
Yeah,
collaborate.
so for example, we know that the singular values of the hypergraphs are skewed. I'm just wondering
Yeah.
if the Ricci curvature values are also.
Yeah.
Thank you.
Thank you, Juergen.